This is Rohini Bawa from Chandigarh Polytechnic College, and I'm working as assistant professor in EC department, that is Electronics and Communication Engineering department in a polytechnic in Chandigarh Polytechnic. So today I'm going to tell you about some things in PCE, that is Principle of Communication Engineering. Let us start with the basic communication system. I'm going to share a screen with that with you all so that it will be helpful in your further studies. So let us start with the a basic communication system. What is a basic communication? So first we all know that what a communication is. The art of sending and receiving, processing of any meaningful information from one place to another by electronic means is termed as a communication. So communication can be done by many ways. It can be electronically, it can be verbally, it can be by understanding our nature, our gestures, etc. So what are some processes of communication? So in this subject, we are going to teach the electronic communication by the electronic means, that is principles of communication engineering. So what is a communication system? With the help of a system, we can transmit our views, our thoughts, our everything, our information from one place to another. So starting with the communication system, here there is a figure shows, or there is a block diagram shown on your screens. So let us start with that. First block is your information source. That what is the information system? Information source. The we can say it is basically the some step to convey a message. We can say that the information source is to convey a message, and this message is originated from the original information source and is selected from the group of messages. The group of messages consist of individual which can be distinguished from one another. These may be codes, these may be symbols, these may be words, these may be group of words and other some coded symbols. Now, next block is our transmitter. So what is a transmitter? We all know that there is an electronic device which can send data from one place to another. Basically, this means a transmitter. But the message from an information source may or may not be in electrical in nature. It is first converted into electrical form with the help of a suitable transducer. Uh, in the next slide, I'll tell you what a transmitter consists of. Yeah, how many things I can say, how many devices, how many electrical circuits a transmitter contains. Basically, it is a encoding, modulation, distortions, and it's a device. Next is your channel. So the signal containing information that is transmitted from a transmitter is received by a receiver before reaching the destination. A medium, that is, it is a medium. Channel is a medium which is required to connect transmitter to receiver, and this medium is known as a channel. It may be a pair of wires, coaxial cables, and transmitting lines, set of transmitting lines, optical fibers, etc. Or it may be a free space also. So next block is your noise. Noise source, that is unwanted signals, distortions, some kind of attenuations like that. These are our noise sources. Next is your receiver. It is a decoding point where communication systems are we are having a different varieties depending upon the system requirements, such as a modulation system use the operating frequency, ranges of a system, types of display, etc. Next one is your destination. Finally, finally we comes to the stage where the input signal, that is a message fed at the information source, is required to be reproduced in the exact manner. That is your destination. But a most important requirement is that the transmitter and the receiver must be common with the modulation and coding methods used in this process. So this is what our communication system is. Information source, a transmitter, a channel, a receiver, destination, and a noise source. Now, starting with what a transmitter is, a basic transmitter. What is consist of? A basic transmitter consists of some blocks, that is, uh, you can see on your screens that it consists of some basic things, that is an information source, source encoder or channel encoder. Source encoder encodes our data, and channel encoder, uh, it also encodes, it transfers the encoded data from source to modulator. Modulator modulates the data with the help of a modulation, which we'll study in our next slide. Then channel comes, it's a medium. After that, we'll come to our demodulator, that is a receiver part. And a receiver part consists of a demodulator, we can say a detector that detects the data, it demodulates the data. After that, again, there is a channel between a source decoder and demodulator, or we can say decoder or a source decoder. So source and then information is synced by the destination. This is what your transmitter and receiver consist of, basic blocks of transmitter and receiver. Now, the next step is modulation. Now, what is a modulation? And the process, it is a process of changing one or more properties, that is amplitude, frequency, or a phase of an analog carrier in proportion with the information signal. It is impractical to propagate information, so it is over standard transmission media. Reverse process of modulation and connecting the modulating carrier back to the original information is known as demodulation. Now, we all have to know that why a modulation is necessary, or a necessity of a modulation. So it is difficult to radiate the low frequency signals from antenna in a form of electromagnetic waves or energy, EM energy, we can say. So we can say we need it for operating range, to manage the operating range, because the power of signal depends upon its frequency. So operating range, there would be a need of modulation. Information signals often occupy the same frequency band that would interfere with each other, and channel is a specific band of frequencies allocate a particular device. Now, one more point, that how modulation is necessary. It is necessary for narrow banding and common processing systems, and sometimes practicability of antenna. So, now, types of modulations. Let us discuss the types of modulations. Analog modulations. In analog modulation, there would be amplitude, frequency, and phase. And in this subject, we are going to teach, or we are going to study the types of analog modulations. That is amplitude, frequency, and phase modulation. Now, what is amplitude modulation? If an information signal is analog and amplitude of the carrier is varied with the proportion to amplitude information, then AM is produced. We'll study later on in this slide, in this also. Now, starting with the FM. FM is a frequency modulation, and if the frequency of carrier signal is varied proportional to the information signal, then FM is produced. Next one is your phase modulation. Sorry. If a phase of carrier is varied proportional to the amplitude of information signal, then phase modulation, that is PM, is produced. Now, analog amplitude modulation, in this it is a method of changing the amplitude of a relatively high frequency signal, that is a normally sinusoidal wave, in proportion with the instant value of a modulating signals. It is to be noted that the carrier frequency remains same and only amplitude varies. In this figure, or in the slide shown on your devices, you are able to see the amplitude modulation. In this, we are having a modulating signal. This is a modulating signal, you can see, having in a red color. Now, next one is your carrier frequency. Carrier frequency is a very high frequency signal that is used for modulation. And next one is your modulated signal. So how we can generate a signal, modulation, amplitude modulated signal. Here it is a normal signal, that is your modulating signal, sinusoidal form, and it is multiplied by the waveform generated from the oscillator, that is a carrier waveform. That is a carrier frequency, we can say, and we'll got the amplitude or a modulated signal at your output. Now starting with its mathematical expressions. Let we'll see, we'll take a modulating signal, that is mt. It can be for in some of your books or some of your journals. You have to notice that, you can notice that the mt will be a message signal, a information signal, input signal, baseband signal, any of the signal. And next one is your am cos omega mt. That is, am will be your peak amplitude of a baseband signal. So the peak amplitude will be this from there to there. This is your peak amplitude of the baseband signal. Omega m, that would be an angular frequency of a modulating signal. And next one is your fm, that is your modulating frequency of the signal. So, in a real life examples of a baseband signal are voice, audio, video, audio, music, video, computer data, etc. Now, let us take a carrier signal. I already told you that the carrier signal is a very high frequency signal, CT. So for its equations, we have to write it like AC cos omega CT. That is, AC is your peak amplitude of the carrier signal, omega C is your angular frequency of the carrier signal, and FC is your carrier frequency. Now starting with the mathematical part, according to the definition of AM, we'll start with AMT, that is equal to AC MT cos omega CT. Now we have to multiply cos omega CT with AC plus MT. Then then it will be AC plus AM cos omega MT. MT we are having in our equation number 1 in our previous slides here. From here we'll put the value of AMT, that is AM cos omega MT in this. Multiply it with the cos omega CT. So AC cos omega CT plus AM cos omega MT into cos omega CT. By rearranging these equations, AMT is equal to AC cos omega CT plus 1 by 2 into 2 AM cos omega MT into cos omega CT. After solving it, we'll came to know that AC cos omega CT plus AM by 2 by solving this equation. This is 2 into 2, and this would be cancelled. Then it would be AM by 2 cos omega MT into cos omega CT. Now, by applying the formula, that is 2 cos A cos B is equal to cos A plus B plus cos A minus B. Apply this formula and therefore this equation. And we have the next equation will be AC cos omega CT plus AM by 2 into cos omega CT plus omega MT plus cos omega C minus omega M into T. By solving these equations, we got AC cos omega CT plus AC by 2 into AM by AC, where AM by AC will be a modulation index. The formula for modulation index, or we can denote the modulation index by MA, and the formula for modulation index is AM by AC into cos omega C plus omega MT plus cos omega C minus omega MT. Now the final equation we got, that would be AC cos omega CT, that would be a part of carrier, plus AC MA. MA is your modulation index, as I told you before. AC MA by 2 into cos 2 pi FC plus FM into T, that is your upper sideband, plus AC MA by 2 cos 2 pi FC minus FM into T, that is your lower sideband. In this equation we got our we contains, or we can say the modulated waveform contains the 3 frequency spectrums. 3 frequency spectrum contains components, sorry, it's not spectrums, it's components. So it's carrier, USB and LSB. USB is your upper sideband and LSB your lower sideband. So this part is your upper sideband and next part is your lower sideband in this. Now come to the power relationships in the AM. So it is PT, PC. PT is equal to PC plus PLSP and PUSP. Here in the figure you can see that it is a LSP, this is a USB, and this is a FC. That is FC minus FM and FC plus FM is your USB. PC is carrier power, PT is your total power, PLSP is your power of lower sideband, or we can say lower sideband power, or USB for higher sideband or upper sideband. So now, what is the total power in AM? It can be calculated as a PT is equal to carrier power plus power used in USB and power used in LSP. That is PC plus PUSP plus PLSP, which can be represented as E square carrier by R, E square USB by R, E square LSP by R. Now, what is this E stands for? E carrier, E USB, and E square LSP stands for your RMS values of the carrier and sidebands of the amplitude. And R stands for characteristic resistance of an antenna in which total power is dissipated. Next one is our carrier power, that is PC, which is given by E square carrier divided by R, which can be further represented as EC by 2 by root 2 whole square divided by R, and it would be PC EC square by 2R. Now here EC is a peak carrier amplitude. I hope this topic is clear to you all. If you have any queries, then you can ask me up. After that, we'll start with a new topic, that is your sidebands. Now, what is a sideband? It is a band of frequencies containing power which are the lower and higher frequencies of the carrier frequency. Both the sideband contains the same information. That is, the upper sideband or lower sideband contains both informations, and it is a band of frequency. Sideband, basically sideband is a band of frequency which is containing power, or lower sideband or upper sideband contains same information. You already know that. Next first topic is double sideband suppressed carrier. So if this carrier is suppressed and a power saved is disturbed to the two sidebands is distributed. If a power saved is distributed to the two sidebands, such a process is called a double sideband suppressed carrier, or we can say simply DSP-SC. In your exams, you have to know the full form of DSP-SC. It will comes in a 1 mark question maximum times. So double sideband suppressed carrier, how it is generated? So it is a MT is your modulating signal, and it is multiplied by the carrier one, that is cos omega CT. It is your carrier signal. This is a multiplier, and after that we got a modulated signal. This is in form of double sideband. Here carrier is suppressed and sidebands are allowed for the transmission. So lower sideband FC minus FM, or upper sideband is FC plus FM. Now how it can be demodulated? So this is a DSPC signal in form of ST. Here it is a product modulator. Product modulator, the frequency generated from the local oscillator, that is your carrier one, which will be multiplied by the DSPC signal. Both signals are multiplied, and after that we got a signal that is the MT modulating signal. And by using low pass filter, you already know that what is a low pass filter? It is a filter which passes the low frequencies only. We got our message signal, original message signal without carrier. So what are the advantages of DSP-SC modulation? So first one, it is provides 100% modulation efficiency. Due to the suppression of the carrier, it consumes very less power. It provides a larger bandwidth. Some of the disadvantages, so it involves a complex detection process. As we have already studied in our previous slide, that was in demodulation of the DSP-SC signal. So the detection process, we used here a multiplier, filters, etc. So the complex detection process is complex, and using this technique it's sometimes difficult to recover the original signal at the receiver. It's expensive technique, and when it comes to demodulation to the signal, in demodulation parts, it's an expensive one. What are the applications where it's used? During the transmission of a binary data, DSP-SC system is used in phase shift keying methods. In order to transmit two-channel stereo signals, DSP signals are used in television and FM broadcast. Starting with our vestigial sideband, it's very important for a 5 marks question. Vestigial sideband modulation is a process where a part of a signal is called a vestige is modulated along with one sideband only. In a previous one, we done both sidebands and carrier is suppressed. In this, along the signal is modulated or transmitted along with the one sideband only. Both of the sidebands are not required for the transmission as it's a waste, but a single band of transmitted leads to the loss of information. Hence, this technique is evolved. Here in this figure, you can see the BSP modulation, that there are two guard bands, and upper sideband and lower sidebands will be, there will be only one transmission, one sideband transmission. Now how we can generate a vestigial signal or a block diagram of a vestigial sideband transmission. Here it is a modulating signal. You all know that it's an information signal. Balanced modulator, which balanced or make to added or multiplied signals, modulating signal with the carrier one. So we got a DSP signal in the output. After that, a sideband filter which only transmits only one sideband, that is a VSP signal, either it is upper or either it is lower. So again, it's linear amplifier which amplifies the signal. Again, that next point is a power amplifier, which is used for transmitting the signal from one place to another with a higher speed. And antenna, it transmits the data or a signal. Now comes to the advantages of VSP modulation. So there are some there are some major advantages that we can say. It is a highly efficient, reduction in bandwidth, and filter design is very easy and high accuracy is needed. After that, the processes a good phase characteristics. The transmission of a low frequency components can be possible without any difficulty. Now there are some disadvantages. You all know that if you are having some pros and cons and everything. So bandwidth when compared to SSP is greater and demodulation is complex. Application, you all know that we used in this can be used in a television signals to transmission of television signals. Next one is your single sideband suppressed carrier system. So the process of suppressing one sideband along with the carrier and transmitting a single sideband is called a single sideband suppressed carrier system, or simply it would be a SSP system. It can be generated with the help of phase shift method, which is a very important method and it comes in your exams many times. So SSP system, you can see here a carrier and one sideband is suppressed and only a single sideband is allowed for the transmission. Now generation of SSBSC. So there is a modulating signal X3 and this signal goes to the product modulator M1 straightly. And some part of the signal, one part of the signal will provide it to the wideband 90-degree phase shifter block. This block, the working of this block is to shift the angle of the signal by 90 degree. That's why it's a 90-degree phase shifter. After the phase shifting, the signal provided to the product modulator 2. And in product modulator 1, there would be a multiplication of the signal, that is a modulating signal is multiplied with the carrier 1, that is a carrier oscillator signal, which is in form of VC cos 2 pi FC3. And other is again signal provides to the 90-degree phase shift, and then after phase shifting, the signal, the output of the phase shifter will go into or provided as an input of product modulator M2. Now the output of product modulator M1 and output of product modulator M2 will be added by enter, which will give us the SSB with a lower sideband. So now the advantages of SSB. So the bandwidth of a spectrum, space occupied is lesser than AM or DSP signals. Transmission of more number of signals is allowed. Power is used. High power signals can be transmitted. Less amount of noise will be present, and a signal fading of the signal is less likely to occur. Some of the disadvantages that the generation and detection of the signal is very complex because of phase shifting, modulators, multipliers, etc. And the signals get affected unless the SSB transmitter and receiver have an excellent frequency stability. Some of the applications, it can be used for point-to-point communications in radio communication, television, telemetry, radar communication, and military communications, etc. Now, starting with the difference, I hope these three methods or methods of transmission, that is DSP, SSP, and PSP will be clear to you all. Are already cleared. So let us compare all three of them. So DSP AC system, less transmitted power than full AM, and all the transmitted power is very useful. In other case, in SSB, good bandwidth utilization, message signal bandwidth, modulated signal bandwidth. And in case of VHP, offers a compromise between SSB and DSP-AC signals. In case of DSP-AC signals, it requires a coherent carrier at the receiver. This results in an increased complexity in the detector. And in case of SSP, a good power efficiency preferred in long distance transmission of voice signals. Next one is your BSP. BSP stands for a transmission standard for a transmission of TV and the standard signals, similar signals. In case of DSPSC, it's suited for a point-to-point communication involving one transmitter and other receiver and one receiver, which would justify the use of increased receiver complexity. The demodulation is harder in case of SSB, which compares to the full AM. Exact filter design and coherent demodulations are required. In case of VHP, bandwidth saving can be significant if modulating signals are of large bandwidth, as in TV and wideband data signals. Now, this contains our whole AM, that is amplitude modulation. Now, starting with the frequency one. In a frequency modulation, the instantaneous value of an information signal is controlled by the frequency of the carrier wave. As you all are able to see on your screens of the figure 1, that is, this is your information signal, unmodulated carrier, which is having a very high frequency, and this is a modulated carrier. Here, the frequency Fi of the information signal controls the rate at which the carrier frequency increases and decreases. So, as with the AM, Fi must be less than Fc. The amplitude of the carrier remains constant throughout this process. And the maximum change in the frequency that occurs to the carrier from its base value Fc is called the frequency deviation and is given the symbol that is del Fc. This sets the dynamic range of the transmission. The frequency deviation is maximum. This question is asked in your 1-mark questions, that what is a frequency deviation. So you must all know that the maximum change in frequency that can occur to the carrier from its base value Fc is called a frequency deviation, which can be given as a symbol or represented by delta Fc. This sets the dynamic range. Now the question arises, what is a dynamic range? What a dynamic range is. So the dynamic range, it is a ratio of largest and smallest analog information signals that can be transmitted. Let us take an example. If the same system were used and the amplitude of the information signal decreased to 1 volt, how would this affect the resulting FM signal? Describe the changes in the space below, including any relevant calculations. So the solution would be, the FM carrier will change in the frequency from 400 kilohertz to 425 kilohertz to 400 kilohertz to 375 kilohertz and back to again 400 kilohertz. Then the signals is having a 3000 times per second speed. So this is because of the frequency deviation del Fc is equal to 1 into 25 kilohertz, that is a 25 kilohertz. And the amplitude of the carrier will remain fixed at the 5 volt. Now, modulation index, it's important one. In the previous one, we already done it for AM. Now it's for FM. It is represented by beta, and it is governed by a modulation index beta, which controls the dynamic range of information being carried in the transmission. The modulation index beta is the ratio of frequency deviation, that is del fc, to the maximum information frequency, that is fi. So beta is equal to del fc by fi. This is your modulation index. So let us see the graph. There is some example so that the how modulation index affects the FM output of for a single sinusoidal information. This is a single sinusoidal information, this one, first one, and the carrier signal has a frequency of 10 times of the information signal. This is a carrier signal. We already know that it is a very high frequency signal. So the graph, this graph or this figure shows that the frequency modulated carrier wave when the modulation index will be 3, that is beta is equal to 3. Now, determination of bandwidth for a FM radio. The FM radio uses a modulation index beta less than 1, and then if the beta is greater than 1, then it is known as a wideband FM, and it, as the name suggests, the bandwidth is much larger than AM. In a national radio broadcasting using FM, the frequency deviation of the carrier del FC is chosen to be 75 kilohertz, and the baseband signal is the high fidelity range, which is having 20 hertz to 15 kilohertz. Thus, the modulation index of beta is, you have to find out. So bandwidth will be 2 into del fc plus fi maximum, that is 2 into 75 plus 15, that is 180 kilohertz. Next example, if beta is less than 1, how a spectrum looks like. The spectrum looks like this. It is having a 2 significant sidebands, and thus the spectrum looks like a very similar to an AM carrier. So it's the spectrum. This is your lower sideband, this is your upper sideband. You already know that fc minus fi is equal to lower sideband, and this is your upper sideband, that is fc plus fi. If the beta is less than equal to 1, then the spectrum contains the sideband, the significant sidebands are increased to 4. If beta is less than equal to 3, then the significant number of sidebands has increased to 8. Now, some additional points to remember. An FM transmission is a constant power wave, regardless of the information signal or modulation index beta, because it is operated at a constant amplitude with symmetrical changes in frequency. As beta increases, the relative amplitude of the carrier component decreases and may become smaller than the amplitudes of individual sidebands. The effect of this is that a much greater proportion of transmitted power is in the sidebands, which is more efficient than AM. Some examples of information transmission using FM. The first one is, let's just take a mobile phones, that because it's used in our day-to-day life. So mobile phones, some of the mobile phone companies use FM with a very low frequency modulation index, that is beta is less than 1. This is known as your narrowband FM, and mobile companies use this because it offers many of the advantages of FM with a minimum bandwidth requirement. Next one is a television sound. In a terrestrial TV broadcast, the video information is transmitted using AM, as we saw during the previous section. This is to make the most effective use of bandwidth available. However, the sound information is transmitted using FM in order to reduce possible interference between the video and sound signals. In this case, the maximum deviation of the carrier will be chosen as a 50 kilohertz, and information of baseband signal is again a high fidelity range, that is 20 hertz to 15 kilohertz. Therefore, the bandwidth requirement for TV sound is 20 hertz to 15 kilohertz. If you have any queries regarding this whole, that is an AM and FM, then you can ask me up, or you can go with the help of the references slides. Have you any queries? You can ask me up. Thank you.